Hi, my name is Brzenski, and this is my presentation using PnetCDF to improve the I/O of large-scale geophysical simulations. All right, large-scale geophysical simulations require access to large amounts of data that is both read and written to physical hard disks. The sheer size of this data makes reads and writes to a disk a significant percentage of a program's runtime. For example, the weather forecast model used by the European Center for Medium Range Forecasting uses a computational grid of 900 million points. And if you were just to save like XYZ coordinates of the 900 million points using floating point integers, the file size for just the coordinates would be 20 gigabytes. So these are huge files. And extra care must be taken too, because these files generally cannot fit on a single hard drive and are usually spread across hundreds of hard drives. Here at SDSU, I've been working with two large geophysical models. Subflow models the chemical and physical properties associated with CO2 sequestration. The physical properties are solved in parallel among up to 120 processes, while the chemistry solver is solved in serial, which means on a single process. And the input-output for this model is done in serial with a single process reading and writing all the data. Here you have an image of, imagine there was some kind of wellhead here injecting CO2, and this would be the pressure gradient in the rock medium after some time period. I've also been working with GCCOM. The general curvilinear coastal ocean model is a large eddy non-hydrostatic Navier-Stokes solver. The solver is fully parallelized using PETSC, but the input-output is still done serially, meaning one process reads the initialization file, and that same process writes out all the data. To parallelize the output, I've chosen PnetCDF. Most geophysical models use a file format called NetCDF. It's handy for writing time series data and for multiple variables and for containers that grow in size. PnetCDF uses MPI input-output routines to parallelize writing using the NetCDF style commands. Using these MPI calls, you can cache a large number of writes and just let MPI decide the optimal way of writing those to a disk. Also, sometimes the data is so large that the address of the variables exceeds what MPI can use, and PnetCDF has a CDF5 file format which uses 64 bits for addressing variable locations in memory. Implementing PnetCDF in Subflow shows a good speed up in I/O times. There's roughly a 50% savings in reading and writing times. The effect of scaling on multiple cores, though, is canceled out by the serial chemistry solver, which parallelizing is currently the subject of ongoing research. That's why this time here stays pretty consistent over the number of processors. GCCOM currently spends a significant portion of its time doing I/O, especially as the problem scales. As the problem scales up to 160 cores, roughly 40% of the time is spent reading and writing data to the disk. Implementing PnetCDF, you can see only 4% of the total runtime is spent doing I/O, and this scales as we go across multiple processes. In total I/O time, or in total runtime, you can see the savings between parallel and serial is eventually equates to the difference between parallel and serial runtimes. Future research on this includes optimizing the MPI I/O hints used by each program and how these interact with the underlying BGFS parallel file system. Some features could significantly increase or decrease the throughput of writing and reading operations. Thank you.